What we want to look at in 17.4 is reaction rates and factors that can affect our reaction rate. So here's kind of a summary of things that we can look at. So the concentration of reactants, pressure, notice this says it only influences the reaction rate of gases. The particle size, sometimes we call this the surface area, or often we'll actually refer to that as surface area, whether or not there's a catalyst, temperature, and light. And normally it's biological reactions that are influenced as far as light, but there can be chemical reactions that we look at as well that can be affected by light. First, though, let's look at how do we measure a reaction rate. What is a reaction rate? Well, one way we can measure reaction rates, here's a sample reaction that's producing a gas. Say we have a calcium carbonate, and that calcium carbonate is being added, or some acid is being added to it. When we add the acid to it, notice we form gas. We've done this before. You form CO2. You also form some water, and whatever our salt in this case is calcium chloride. What we can do is we can measure the volume of gas that is formed over time, and we can plot that on a graph, and we'll get kind of a curve that looks like this. So notice this is volume of gas formed straight from our gas syringe, and this is over time. So at every maybe 30-second increments on our stopwatch, we're going to measure the level of gas, level of gas, level of glass. Notice what this graph gives us. And I'll erase it. It's not a linear relationship. What you see is the reaction is almost always fastest at the start. So we have initially a very fast reaction that slows down, until notice the volume of gas plateaus. It plateaus because we're not making any more gas because the reaction is completely done. So that is the end of our reaction. So one thing we can measure in lab to find a reaction rate is how much gas is being produced over time. And notice we can measure that rate in cubic centimeters per minute or cubic centimeters per second, however we want to calculate it. So that's one thing we'll notice on reaction rates is the units that our rate is in is kind of dependent upon what we're measuring and the best way to measure it. So that's producing a gas. Now here what we have is same type of reaction. This one has the hydrochloric acid reacting again with calcium chloride, our marble chips as they call them. And again, it's still producing gas, so it's the exact same reaction, but here we're measuring the effects in a different way. Here, there is some wool on the top, so that means the CO2 can release, and we're not catching the CO2. What we're doing instead is the CO2 leaving is going to cause the overall mass to decrease. And so again, we need to have our stopwatch. And at certain time intervals, we would read off what this mass is. And notice we also get a gradient here. And again, it's a curve. It's not a linear relationship. Again, steepest at the beginning because our reactions are always quickest at the beginning. And it slowly plateaus until it doesn't lose any more mass because the reaction has stopped. So a couple different ways. We could measure the volume of the gas. We could measure the mass decrease. And based on these, we'd have different rates. Now, if this one we wanted to write a rate in, this one would be grams, or grams lost per unit time, perhaps minutes again. So we can have different rates again, depending upon what we measure and how we determine that rate. Now, a lot of things are actually going to be, this one's in number of molecules, but a lot of them are going to be in concentration. They would really like to measure this in units of concentration. And when we actually calculate reaction rates, they'll almost often always be in units of concentration. Now, if we notice this reaction, and this is very similar to the others, we have a chemical reacting. We'll say this chemical is just, say, decomposing. Maybe it's hydrogen peroxide, and it's decomposing to hydrogen and oxygen. Well, there's only one unit there, so it's not super clear of what it is. But notice purple is our reactant that we start with. Notice we start with, in this case, 50 molecules of it. Notice what happens over time is changing to green. But where do you see the majority of the change happening? You see the majority of change happening in this first step. Now notice almost half of them go green, a little bit more go green, and now notice in these steps there's very few purple ones left at all. So that's displaying the same fact that if we plot this graph, we're going to have a very steep line at the beginning. Reactions are always fastest when they start because there's the most stuff to react with. Over time, that reaction rate decreases again until we plateau out and we don't form any more product or we've used up all of our reactant. So we're going to see similar reaction rates are similar looking curves. Now, what's going to affect those curves, though, are the factors we are looking at in the first line. The first one I want to look at is temperature. So what does temperature do? Well, remember, temperature, obviously, is related to the kinetic energy. Kinetic energy, again, being 1/2 mv squared. So we're really looking at the velocity of the molecules. So if we increase the temperature, we increase their velocity. If they have more velocity, it's more likely that they're going to form effective collisions. Now, remember from the last one that just because they're colliding doesn't mean they're reacting. They have to react with enough energy to get beyond that activation energy and in the right orientation. Now, we can't orientate them with the temperature, but we can cause them to collide more. The more they collide, the larger the percentage, the larger number, just sheer number of positive collisions that we'll have. So notice if we raise the temperature, we push the fraction of molecules that are beyond the activation energy higher. So at low temperature, we have a very small amount of particles that are possible to react. As we raise the temperature, and if we raised it more, we're going to have more and more molecules that are beyond that activation energy and have the proper amount of energy to collide and react. Now, we do have to be a little bit careful. Now, this is for the vast majority of reactions. We do have to be careful that some reactions that produce a lot of heat, if we put them in a warm environment, it'll actually slow down the reaction rate. But that's not as common. That's more of an equilibrium effect on the reaction. So for a basic understanding, increasing in temperature raises the number of molecules that are beyond the activation energy and is going to increase the rate. Okay, what else do we have? Nothing there. Surface area. Okay, if we have the reaction here, and this is a reaction of magnesium reacting with hydrochloric acid. In this case, these are representing the hydrogen ions. Well, if we have a strip of magnesium, the hydrogen ions really can only react with the outside layer that they can see. They can't react, notice, like with this, with the molecules that are inside. The outside surface has to react first, and then the inner surface and the inner surface. But if we take that magnesium ribbon and we cut it into smaller strips and smaller bits, now there is more surface area. So we can have the same number of hydrogen ions, but those hydrogen ions have more areas to react. So an increase in surface area is going to lead to an increase in the reaction rate. So we're going to have an increase of reaction rate. So we increase in temperature is going to increase our reaction rate because our molecules are moving faster. More of them are beyond the activation energy. An increase in surface area is going to increase our reaction rate because there's more surface to react, more places that, again, have positive collisions. It's always about having the correct number of collisions. So notice this is an example of a reaction rate with a large surface area and with a small surface area. So our large marble chips, before they're crushed up, have a very small surface area in reference to their overall volume. If we take those that have a small surface area and we crush them up, well, then our chips are small, but we've increased our surface area, and now we have a large surface area. And so what we'll see is if we look at a reaction rate, this is measured in loss of mass over time. Notice this one has a steeper graph initially and stays steeper until it plateaus out. Now notice a couple things with this graph. So this has a steeper initial rate. It stays steeper than the one with the low surface area, the big chunk of marble chips. But notice they both finish at the same spot. So even though we're increasing the reaction rate, increasing the rate doesn't change how much is actually created in the end. We're still going to have the same numbers of products. We don't change how much is formed. We just change how fast we get to that point. Now notice here's another one I don't have a good slide for. So we've talked about temperature changes, increasing the reaction rate, surface area changes, increasing the reaction rate. We can also have changes in concentration. Changes in concentration are actually going to put kind of more stuff in the area to react. So here's a reaction rate graph of the production of CO2, of calcium carbonate, again, reacting with hydrochloric acid, our generic example for all of these reaction rate calculations that we're looking at. Now in this one, in the first one down at the bottom, you have 0.5 molar hydrochloric acid. Well, if we have 0.5 molar hydrochloric acid, notice we have this slow rate, almost a line until we get and produced all of our CO2. Notice if we double it, we get a quicker reaction rate. We have a steeper curve, a faster initial rate, And if we double it again, we get an even steeper curve. And so increasing the concentration, we have more stuff that's available to react. Notice, if we have a certain amount of calcium carbonate, we're still only going to produce the same amount of stuff. So again, it doesn't affect the amount of stuff that we produce. It just affects how quickly we get to the end of the reaction. Notice this reaction ceases right here. We've reached that plateau. The 1 molar ceases right there. And this 0.5 molar doesn't reach that plateau till way down there. So what we're doing is really increasing the rate, again, not increasing the amount of stuff. So an increase in temperature can increase the reaction rate. Increasing the surface area gives more places for collisions. Increasing the concentration, again, it's all about increasing the number of collisions. Last thing that we can do is we can add a catalyst. What a catalyst does is it lowers the required amount of activation energy. And now that's a really kind of bland, boring definition because it depends on what type of catalyst to look at how exactly that occurs. Sometimes the catalyst is actually a surface that the molecules will bind to. Sometimes the catalyst kind of provides some extra electrons that can float between energy shells to make things happen faster. But what it does overall in all of the examples is it lowers the overall activation energy. So if we have a normal, notice, exothermic reaction where we have, say, hydrogen again and oxygen, this is an example we like, it has to get over this bump to go down and form water. Overall, it's an exothermic reaction. If we have a catalyst for that reaction, the catalyst for this reaction actually, we would throw it in, and it's going to lower that energy path. So we have a place to produce water, but we don't have to put in as much energy to get the reaction to occur. Now notice the net energy released by the reaction is the same. It has the same energy, the enthalpy of formation, we could say, but the process to get there has a lower amount of activation energy. So we've looked at these things: concentration, particle size, catalyst, and temperature. Pressure, we don't get into quite as much, but if we push all the gas molecules together, they have a better chance of colliding. And a lot of times light, again, acts as a catalyst to get things to chemically react. A lot of times it produces oxygen as a radical, especially if we have ultraviolet radiation, but we don't see a lot of those examples in our book this time.